Lesson 18, Acceleration. Our objectives. First, as usual, we want to define what it is we're talking about. Secondly, you'll want to be able to calculate acceleration, final velocity, or time using this definition. So let's start with the definition. Acceleration is the rate at which your speed is changing. One of the ways that you notice when something is accelerating is, for example, if you're in a car and you look at the speedometer. If the speedometer needle is moving, the speed is going to be changing. And that includes whether the needle is moving upwards as you're speeding up or going downwards as you're slowing down. As long as you have a change in speed, if we find the rate at which that speed is changing, we're determining acceleration. The symbol is a lowercase a. Now, it's very important that you use a lowercase a, because a capital A is used for area. We only have 26 letters in our alphabet, 52 if we say capital and lowercase. If we use a symbol, and it's a specific symbol, such as this, it's important, because if we decide to use, say, a capital A, there's another formula that looks very similar to some other formulas that involve acceleration that use area instead, and it can be very confusing. So scientists have agreed to use a lowercase a, and you should always use a lowercase a and not a capital A for acceleration. For our formula, since acceleration is the rate at which speed is changing, we get something that looks like this. As a rate, notice that we are dividing by time, but it's the rate at which speed is changing. So we have two different speeds. We have a final speed or velocity and an initial speed or velocity. We indicate the final speed or velocity as a v with a subscripted f for final, and the initial velocity with a subscripted I for initial. We take the difference between the two before we divide. Notice the parentheses on top. The parentheses are important mathematically because a lot of times if you do not put the parentheses in, you will not get the correct answer. Now, since there are 4 things in this formula, we can't make a triangle to make things a little bit easier. So the algebra is a little bit messier. So we can rewrite the formula to solve for the final velocity or the time. You'll want to put these 3 formulas on your formula card under mechanics. Label it acceleration. They will all be formulas that involve acceleration. They're just rearranged, solving for acceleration, final velocity, or time, depending on the situation. For the units, since we are taking something like meters per second and dividing by a time, seconds, we get meters per second, or meters per second squared. The seconds don't cancel. They actually combine. So as a shorthand way of writing that, we put seconds squared. This is also one of the few times that it's okay to mix time units. Whenever we accelerate and we're talking about speed, speed is going to be in something like miles per hour, but accelerations occur over seconds. They don't occur over minutes, and they definitely very rarely ever occur over hours. So we can write something like miles per hour per second or kilometers per hour per second, depending on the situation. Something else to take note of is something I mentioned earlier. Acceleration is the rate at which your speed is changing. So if you're looking at your speedometer needle, it can go up if you're speeding up, or your speedometer needle can go down if you're slowing down. If your speedometer needle is going down, you're decelerating. In that case, you're going to be taking a smaller final velocity and subtracting a much higher initial velocity, giving you a negative value. So for us, deceleration will generally be noted as a negative acceleration. In other words, negative signs are going to be important when you're doing these problems. Let's take a look at an example. A motorcycle starts from rest and accelerates at 5 meters per second for 10 seconds. What is its final speed? So when looking at this problem, we start by looking at the question. We know that we're looking for the final speed. And the only formula that we have that involves final speed is our one involving the acceleration. So we put that down. Now notice, for this, we need the initial speed, the acceleration, and the time. And it tells us that it accelerates at 5 meters per second. So that's our acceleration. For 10 seconds, seconds indicates time. So t equals 10 seconds. But we still need an initial speed. So notice at the beginning of the sentence, it says that it starts from rest. This is one of the situations where words are going to tell you things. In the real world, when we take measurements, we don't always have things that give us numbers, and we have to be able to determine values from words, and this is one of those situations. So it's very important to not just look at a problem and try to grab numbers. You have to read the problem carefully. Starting from rest tells us that our initial velocity is 0. You will get other problems that say things like coming to a stop or coming to rest. That means your final speed is 0. So read the problems carefully. Now to continue with the problem, we have our values so we can substitute them in. Notice I did put the units in. That can make it a little bit easier. In this case, we're taking meters per second and we're adding meters per second squared times seconds. When we do that multiplication, we can see that the seconds and the seconds squared cancel to give us meters per second, so that we now get 50 meters per second for our answer.